the recording. First emailed question, how does 9/10 turn into 8.8? So that's this guy here. So if I, and I do apologize that the videos weren't up. I thought I had clicked the last button to actually make it happen last night, and I came back this morning and I hadn't done that. So this morning they are now uploaded, or in the process of uploading. Let's look. Where are they? Are they up? Come on, YouTube, figure yourself out. The encoding is overloaded. I'm going to pause this. Okay, back to you. The question I'm assuming was coming from this example here, where I've got 15/17 became 18/20, became 9/10. What you need to remember, though, is for this example, we started with a whole number. This thing here is a mixed number. It's 8 and 15/17. So 15/17 becomes 18/20. This becomes 8 and 18/20, which makes this 8 and 9/10, which is where we get the 8.9 from. So that's the chain of reasoning that leads us to 8.9. So I do apologize for that. That wasn't abundantly clear. Thank you to the mystery person for sending in the email question. The next one comes to us from this classmate. I don't really understand the concept of estimating square roots that are less than 1. So here we go. Let's flip. I got another example here that we can do. I believe I'm just making a small mistake at some point during my calculations. Wondering if you could quickly go over it again. Happy to. Let's do that now. I think the way you explained it today would be able to help again, but the recording today hasn't been uploaded. Yeah, my apologies. Yeah, that was my bad. So maybe this will help. I'll talk about the big numbers first, and then we'll talk about the decimal numbers second. For the big numbers, again, we start wherever the decimal place is going to go, and I hop until I'm at the beginning of that group. So for like this guy, if I were to do this one here, the decimal place is here. I hop a group of 2, and now I'm at the beginning of what would be the next group. And when I say the beginning, I mean like the lowest place. In this case, I would be estimating the square root of 5, and we'd go from there. I'm not going to do it all, but we'd estimate, yeah, we'd be doing 5. For this guy here, I'm at the decimal place, and I want to take it to the beginning of the non-zero group closest to the decimal place. The beginning of that group is still that right-hand side. So I'm still going to jump this thing once, and now I'm at the beginning of the first 2-digit non-zero group. The beginning being on the right-hand side of what is now 45. So we're going to estimate the square root of 45 here as the decimal. And this is the one that I'm going to go through now in more detail. So we've got the square root of 45 is the one, it's not equal to, I'm going to put an arrow there. The square root of 45 is the one that we want to estimate. The square root of 45 is between which two perfect squares? 45 is between which two perfect squares? 36 and 49, which means the square root of 45 is going to be between the square root of 36 and the square root of 49, which means it's going to be between 6 and 7 somewhere. To figure out now how far along the way this is, we need to figure out what this distance is. From 36 to 49, if I'm not mistaken, that's 13. And from 36 to 45, that's 9. So my estimate now becomes 6 and 9/13. Well, I don't know my 13ths fractions. I don't expect you guys to do your 13ths fractions, but I do expect you to do this with the calculator. So what is a fraction that we could massage 9/13 to be nicer to simplify? I could go down to 8/10. There's actually a closer one we could do. Presley? I could do 9/12 because 9/12 is going to simplify really nicely to what? 3 over 4, which is 0.75. So I could make this 9/12. I could make it 8/10. That's 0.8. I'll do that down here. I don't have a lot of room there. So this one, bless you, was going to round to 6.75. This one's going to go to 6.8. Both of them, I mean, these are fairly close estimates. Both are acceptable. I would not say I would take one over the other. If one of you gave me this one and one of you gave me this one, it's still possible for both of you to get this thing right. It's just an estimate. So then what we need to do now is we jump the decimal back 1 for every group of 2 we hopped. We hopped one group of 2. So from 6.75 or 6.8, I'm going to drive the decimal place 1 back to the left, which makes my estimate either 0.675 or 0.68, depending on which of these fractions I used. Now, could someone punch 0.75, or the square root of 0.75 into your calculator and tell us what it is? Sorry? 0.45. What is the square root of 0.45? 670? Well, that one's looking pretty good. Does that help everyone? I'm looking for a nod from a specific person, but I want nods from everybody if this works. Okay? I will always, if you email me in questions to answer the next day, I will always deal with them anonymous unless you specify that it doesn't matter. So thank you to the 2 of you who sent me. Are there any other questions about the homework? Okay, then I'm going to go over the homework. I'll show you what I did for the questions I assigned. It was those ones, and I assigned them. So here's what we had. Again, your estimates don't need to be exactly what my estimates are, but they need to be close. So this is what I assigned unto y'all. Again, the estimates just need to be close. They don't need to be exactly what I have. Comments, questions, concerns about any of these? Yes, Carolyn. Sorry, which one? Oh, part 4, number, just any of them? Number 3. So you got 12.5. How'd you get 12.5? So you jumped once, and there it is. So you found the square root of 2. So that's going to be 1 between 1 and 4. So the square root between 1 and 4 is, well, that's going to make it between 1 and 2 because the square root of 1 is 1. So this distance here is 4, and that's 1. So that became 1.25. So that becomes 12.5. Yeah, that's cool. That's fine. Yeah. The way I did this one is 254 is still small enough that I know what that perfect square is, like what the closest perfect squares are on either side there. And so I just went straight to a slightly larger one. But that for these ones, I'll be looking at your technique, and as long as you use one of these techniques and give me a reasonable estimate based on the techniques I've given you, you'll be fine. Anything else? Comments, questions, concerns, queries, conundrums, consternations? Query. No queries? You guys know what a query is? Query is a question. Statement of interest. Yeah, Carolyn?
So I've got this one more question about part 4, slide 11.
Okay.
I was in the wrong. No, it was my fault. Sorry.
You're good?
Yeah.
Okay. Number 11 is an interesting one because you need 2-digit groupings. So if we jump the decimal 1, 2, 3 times to a 2-digit grouping, the estimate now is not 6. The estimate has to be the square root of 60. Because we need 2-digit grouping. So then you estimate the square root of 60. And then you go from there. Okay, comments. Any further comments, questions, concerns? Moving on, once, twice, 3 times. So here we go. Do we know our perfect squares? How many do we know? Maybe we should make a list. Let's make a list of perfect squares. We're going to make our lives a little bit easier here. Where do I want to put them? Let's put them here. Okay, so right at the top here, we're going to make a list of perfect squares. Perhaps something we could have done yesterday. But we're going to do it today to make up for the fact that we didn't do it yesterday. Bam. And we're just going to go along the top because I haven't given you any other space to work with it. So a perfect square is, well, the integer perfect squares are the ones that we're going to concern ourselves with today. So they are an integer times itself. So the easiest perfect square, the nicest perfect square is what number? 1. Thank you. 1 is 1 times 1. What's my next perfect square? 4 is 2 times 2. 3 times 3. 4 times 4. 5 times 5. 6 times 6. 49. 7 times 7. 64. I hear it from a few places. It's good. 81 is 9 times 9. 100. Keep going. 121. 144 is 12 times 12. This is where there should be zero hesitation getting to this spot. This is where things might get a little bit fuzzy for some of you. How many of you can go further? Okay, so this is, well, let's keep going. This is what the bare minimum expectation up to this point. Now we're going to commit some more to memory. 13 times 13. Oh, we know this. This is good. 14 times 14. Cool, 196. 15s are? 15's easier than 14. 225, good. 16s are weird. Actually, if you're in a computer, 16 should be easy. It is 256. Who said that? Gavin. That may be true. I don't know. It's quite possible. So that's the 16s. And yeah, everything is in multiples of 8s and 16s in computing bits. So 256 might be one that you recognize. 17 squared. The only reason I know 17 squared is because these 3 digits used to be in my license plate. And I looked at my license plate. I'm like, that number looks familiar. And I punched it. I'm like, oh, yeah, no, it's totally 17 squared, which is awesome. 17 squared is 289. Now we're getting into the weird ones that I don't necessarily expect you to remember. 18 squared is 324. 19 squared is 361. 20 squared, though, should be easy. Because 2 times 2 is 4, so 20 times 20 is 400. And beyond that, I don't expect you to be able to, or I won't expect you to have to do without a calculator. But you should recognize this list. And if there are ones in there that are like, I mean, you've done up to here already. And so what's one more? 13, 14, 15, 16 is nice and easy, which means you've really only got 3 gross ones. But, you know, I've told you now all my license plate stories, so that's going to make 17 squared memorable. Oh yes, my math teacher's license plate, the 3 digits were 289. That means that leaves you only 18 squared and 19 squared, which is 324 and 361. So really, it's not a lot to ask. Okay, so you're going to want to recognize these first 20 perfect squares to make your life a little easier until I let you use a calculator. So now here we go, working with squares and square roots. Let us carry on carrying on. So, working with squares and square roots. How are squares and square roots related to each other? When I say squares, what do I mean here? Sorry? A number times itself. What mathematical operator do we set up to deal with that? It is yes and no. When you say a number times itself, that's multiplication. When I say I'm squaring the number, that's an exponent, power of 2. How are squaring something and square rooting something related to each other mathematically? I want to give my square roots a square root sign. So there's me square rooting. How are squares and square roots related to each other? I see that hand, Rebecca. It is not dividing by itself. No, because that would give you 1 every time. A number divided by itself is 1. It's a good guess, though. Carolyn, how are they related?
I don't know the English word, but like multiplying and division, like I don't know the word.
One is multiplicative. The other one is not division, though. Square rooting doesn't divide in the traditional sense of division. What does square rooting do? Square rooting, you give the square root a number, and then you take a number, you shove it into the square root, and then it gives you back what number multiplied by itself. So what number could I square to give you the number that you put into the square root to start with? So you put in 64, you're going to get out 8. Why? Because 8 squared is 64. Okay? So we've got 2 operators here that are undoing each other. One takes the number, multiplies it by itself. The other one takes the number and tells you what number you had to multiply by itself to get it. So when I've got 2 operators that undo each other, we've already used this word before. Are they related to each other? Yeah. They are inverses of each other. They are inverse operations. These 2 operations are inverses, which is going to help us here momentarily. How is this going to help us here? Well, I'm going to now have to start evaluating these kinds of things. 2 root 9 plus 3 root 81 divided by 11. Now, without the roots there, this looks an awful lot like what kind of style of question that we've already done? Bedmass, order of operations. But now I've got the roots in here. Where in bedmass? There's no R in bedmass. Where do the roots go? Why exponents? Not only are they similar, they're exact inverses of each other. So if multiplication and division were together and can be done in either order, it makes a lot of sense that these roots would go where the exponents go. That is a great thought, and you're absolutely correct. We could take bedmass. We could change it if we wanted to add now these roots in here. We could call it bread mass. But we're not gonna, because no one else, you'll be like, oh yeah, bread mass. And in Math 10, Mr. Myers is going to be like, huh? No. But you could, because the roots are going to go in there. And we're actually have another name for root here in a second. So this, I love it. This is where the roots go, or where the roots get dealt with. And just for fun, if you want to take this to math next year, and yeah, just throw bread mess at Mr. Myers and see what he does with that. Absolutely. Happily. Go for it. I wouldn't tell you to do something if I wasn't fully prepared to take the responsibility for it. So let's deal with this. Now, let's go through it. I've got 2 root 9 plus 3 root 81 all over 11. So there's no brackets. Are there exponents? Well, not really, but we've said that now roots, because roots and exponents are inverses of each other, we're going to deal with the roots where we deal with the exponents. So that's what's going to happen first. So when I simplify this, what am I going to get after my first step of simplification? Let's deal with the roots. Sorry, Ty, was that you? No. It was Jay? You have a thought? Sorry, it's become 2 times 3, because the square root of 9 is 3, absolutely. So this is going to become 2, and the square root of 9 is 3, so I'm just going to toss a 3 there in brackets, plus 3, and the next, I'm just going to do both simplifications together. The square root of 81 is 9. Sorry? This 3, because this is 3 times the square root of 81. So when the square root of 81 is 9, this just becomes 3 times 9. So now BEDMAS says I do what? Multiplication. You've got to be careful here. It does say division technically comes first, but when I've got a whole bunch of things going on, an expression in the numerator, it's equivalent to this being true. But I've got a set of brackets up there, so I want to deal with the entirety of the numerator first. So now let's deal with the multiplication. 2 times 3 is 6, plus 27 over 11. Now I'm going to deal with the addition in the numerator. We're going to speed this up a little bit here. 6 plus 27 is 33 over 11. Now I can go back and deal with the division, because now I'm done dealing with the numerator. 33 divided by 11 is 3. Cool. Comments, questions, concerns? Queries, conundrums, consternations? Okay, love it. Done. What do we do with fractions? You guys did exponent rules last year, yeah? A little bit, grade 8. Some exponent laws? None? That's not true. You had an entire math year and you didn't do exponents? Hands up if you're like, yeah, we did exponents. Not nearly enough hands. Okay. Well, let's go through it again. Yeah, Carolyn, you were back in Germany last year? Yeah. Germany's, yeah. You likely did these a long time ago. So, here we go. For those of you who have never seen the exponent laws, this isn't going to make a lot of sense to you. For those of you who did see exponent laws, a couple of you, did you do an exponent law for when you had a fraction to a power? What happens if I have a fractional number to an exponent? Did we look at this? No. Bad. Harwin. It was a good guess though. Okay, so we're gonna tweak this here because these are related to. This is gonna be important later. Let's deal with this. What if I had I have 2/3 and I square it? What does that mean mathematically? Well, you guys said earlier, yeah. Yes. Squares the top, squares the bottom. So this is going to become 2 squared over 3 squared. So this is going to become 4 over 9. This is ringing bells back in the past, a long distant memory. Okay. Love it. Hands up if this, more than just Aminette, this is ringing some memories of a long time ago. Awesome. A few hands are going up. I love it. So because roots and squares are inverses of each other, the same thing can be done here. when I'm taking the square root of an entire fraction, I can take the square root of the numerator and divide it by the square root of the denominator. Just like I could apply the exponent onto the numerator and the denominator, I can apply the root onto the numerator and the denominator. So the square root of 4 is 2, and the square root of 49 is 7. So the square root of 4/49 is 2/7. Where did I lose you? Some of you are like, oh yes, the lights have been turned on, and others of you are fading into the dark. So where is this confusing? We're not, you don't use that word division. We haven't divided anything. We're going to do the middle one in a sec. I'm just letting a few people explain things to their neighbors here. I'm totally content to take a couple seconds for you guys to explain it to each other if you don't want to ask in front of the whole class. I love that. Assuming that the person who's helping you knows what's going on. Okay, let's do the next one. So the next one, this follows the same rules as bed math. So what do I do when I have negative square root of 16/81? Well, that negative out front is the same as what mathematical operation? Timesing by -1, you betcha. So I can rewrite this as -1 times, I would never do this if I'm actually doing the problem, but this is how I want you to think about it. Negative out front is the same thing as multiplying by -1. So it's going to impact how you do bed maths. In this case, if I've got a negative just sitting out front, I'm still going to deal with the roots the way I deal with the roots, and then that negative gets applied at the end. So if I have the square root of 16/81, this is going to become -1 times, well, this is going to become root 16 over root 81, because I can split up my fraction in the roots. So this is going to become -1 times 4/9, which is just going to make my final answer, I'm going to go up here, -4/9. And conventionally, that negative either goes with the numerator or just kind of in line with that line in the line in the fraction. It almost never, like 98% of the time, you do not want to put it into the numerator, the denominator. Don't put it in the denominator. Okay, next one. I have the square root of 50/72. Looks like fun. Is 50 a perfect square? 72 a perfect square? So at first blush, we look at this and we say, I probably can't do this. But there's something, when you're dealing with fractions, there's always something you want to see if you can do first. Before you give up, simplify it or reduce it. Can you reduce 50/72? If I divide both of them by 2, it's going to give me 25/36. Interesting. Are either of those perfect squares? Yeah, they both are. Fantastic. So I can actually take the root of 50/72. It's the same thing as 25/36, which means I'm going to take the root of 25 over the root of 36, which is going to give me 5/6, and we're good to go. So we're going to make a note here. Reduce first if you can. Reduce or simplify. I'll use those words interchangeably. Okay, next one. Determine the square of the following numbers. What's that asking me to do? Yeah, who said it? Louder. That was the correct thing, Rebecca. Multiply it by itself. So the language there is really important. If I ask you for the square root of something, you're finding numbers that multiply together to give you the number I gave you is the question. If I say determine the square of the following numbers, you're just going to take the numbers, you're going to multiply them together. So this one should be relatively easy. The square of 0.9 is what? So it's going to be 0.9 times 0.9, which is 0.81. Careful, it's not 0.9 times 2, it's 0.9 squared, which is 0.9 times 0.9. 9 times 9 is 81, so 0.9 times 0.9 is going to have two decimal places, 0.81. 2/5. What's the square of 2/5? You leave it as a fraction. It's not 2/5 is 0.4. I want the square of 2/5. Thank you. 4 over 25. Because I'm squaring this thing. Okay, how about this guy? Negative 0.8. What is the square of that? While that is correct, I want you to be really careful. I don't need to know who said it. Don't out yourself, because I'm going to correct whoever it is here in a second. We want to be really careful not to say things like 0.64, because that actually implies certain things about the number that are not true. Because if I have 0.60 here, and here's the problem that I run into with students who say things like 0.64. Okay? The problem is you get to a number like 0.99, which is 0.99 is how you're supposed to say it. If you increment up from 0.99, the temptation is to go to 0.100. Is that correct? No. The next number should be 1. So when you say things like 0.64, it opens you up to making mistakes like that, and especially in a test situation, when you're going really quick, that's a really easy way to screw up. So the language you choose to use is really important. I don't know if your middle school teachers have ever come down on you for things like that. I said it on like the first or second day, I might be the first like true math teacher you've ever had. I have a master's in this stuff, so I'm going to be real neurotic about the words you choose to use here. 0.64. It's going to save your life. Negative 3/7, what's the square of that? 9/49, or 9 over 49. Cool, I love it. Anyone, comments, questions, concerns? Okay, cool. Let's go have some more fun, because if this isn't fun enough. We're going to apply this to the bigger and badder and better. Okay. We've cubed things before, yes? Do we know what it means to cube something? To the power of 3. So what do you think so here, let's do this. So a square root, no, let's not do this. Let's go all the way down here. I'm just going to add something in here. Cubing. Maybe it makes it easier to think of it this way. Cubing is, how would you explain it if you had to explain it to someone? Multiply a number by itself 3 times. Cool. Like that. So what do you think cube rooting is? Have we cube rooted before? No. Okay, well, if some say yes, lots of shaking heads. If cubing is multiplying a number by itself 3 times, what's cube rooting? It's not dividing. Sorry. I want just the voice over here. Find the number that multiplies by itself 3 times to give the number you started with. Or the number you, I'll say this, the number you cube rooted. Sometimes I try to explain cubing and cube rooting rather in terms of square rooting and perfect squaring. But this seems to work for you guys. Cubing and cube rooting. Before we go a lot further, has anyone ever stopped to think about that word root? Why do we call this thing square rooting? It's not the root of the number, believe it or not, but it is the root of something. It's the root of, so, I think I just heard, say it again louder, if you just said something. It's the root of, maybe you're just trying to be silly, but I think you're actually right. I could have sworn I heard it. So if I'm square rooting, it's not the root of the number that I'm looking for. A square root is going to give me the root of a square. Was that Carolyn? Did you say this now? Okay. And when I say square, I mean a literal square. Did someone say that back there before? Yeah, Jay said it. See, Jay, you should have committed, man. Double down. Okay, so a square root. And this comes from ancient Greek mathematicians. Give a bit of a history lesson here. I'm going to give you little history lessons all the way through this course because two of my favorite courses that I've ever taken were history of math. I did one as part of my master's. I did one as part of my undergrad. So I got a lot of random stories like this. So square root, where a square root comes from is they would take a number, these Greek mathematicians, and they say, well, can you make a square out of this particular number? And so the perfect squares were the ones where the area of the square had side lengths that were integers. So if my area of this square is 64, the Greek mathematicians, obviously they're using Greek, not English, they would say, okay, what is the root of this square? I.e., and then what they mean by that is, what is the length of the side that will make me this square? Well, we know that the area of a square is the length times the length, which we also write as this. That's length, that's a length squared. So what number times itself gives you 64? 8. So they would say this side length is 8 and this side length is 8. So the root of this square, i.e. what is the side length that gives us this area, is 8. And that's where this idea of square rooting comes from. That number 8 is the root of the square, aka, which means also known as, the side length. Okay? So that's where this idea of square rooting comes from. So, just stab in the dark. What do you think a cube root is? Someone said triangle. It's not a triangle. Which would give us what shape? Assuming that the length and the height are all the same length. It would give you a cube. Very carefully. So now we're not dealing with areas. What are we dealing with when we have a cube? Sorry? Volume, thank you very much. So for example, if the volume of this cube is 27, what is the side length? Well, volume for a cube is the length times a length times a length. So what number times itself, then times itself again, is going to give me 27? 3. So you can give me a length of 3. I'll say a side length, rather, of 3, also known as the root of the cube. Yeah. Because 3 times 3 times 3, 3 times 3 is 9, times 3 is 27. And these lengths all have to be the same. How do you write a cube root? That's a great question. When we did square roots, let's go back up to a square root. What was the notation we had here for square roots? Yeah, kind of a weird looking lightning bolt thing. So notationally, we had this. I'll draw a line right here. Notationally, we did this. We're going to get technical. This is what it looks like. So a cube root needs similar notation because it's similar mathematically. Similar notation is going to give us this. We're going down here. I want you to take note. There is a lovely little space that needs some decorating, shall we say, right here in the square root. So what we're going to do is we're going to use the same symbol, but we're going to insert a lovely little decoration into that little spot. We're cube rooting, and so we're going to represent that by having a 3 in that little spot.
So a square you could also write.
You could. You could. There are things in math where if we don't write them, they're assumed to have a known value. So like if I have a set of brackets and there's no number out front of the set of brackets, you could assume that what number is multiplying there? 1. Or if I have a variable with no number out front, that number out front is, if I have just like an x, how many x's do I have? 1. I don't have to write the number 1 there to know that there is 1x. Similarly, with the square root, if I don't write a value there, it's assumed to be a square root. As soon as I want anything bigger, I'm going to run into this cube root here. We're going to run into a problem in a sec here. If this goes from 2 to a 3, is there any reason why I can't have larger numbers here? Square root was what number times itself twice. Cube root is what number multiplies by itself 3 times. Are we limited to that? No. I could go to what times itself 4 times, or 5 times, or 6 times, or 7 times. And the math still holds out. I could have 4th roots, 5th roots, 6th roots, 7th roots. And in fact, I'm going to take you guys up to 5th roots. It's going to be fun. It's going to be great. You're going to love it. We'll show you how I do that in a second. So we've got the cube root going on here. What do I want to say about the cube root? I was just going to say something here. Oh, that's what I was going to say. The square root and the cube root have nice physical representations. A square root is literally what is the side length of the square. A cube root is what is the side length of the cube of a given volume. As soon as I talk about 4th roots, now I need to jump into a 4-dimensional shape. Is that possible? No. So now, jumping up past cube roots, we no longer have nice physical representations to think about, but the analogy, the mathematics still holds. So one thing I want to address here, let's talk about perfect cubes. We're going to make a list at the bottom of this page. Just like we made a list on the top of the previous page of the perfect cubes, I want to make a list now, sorry, of the perfect squares, I want to make a list now of the perfect cubes. So this one's going to be a lot harder because these numbers are going to get real big real fast. The first perfect cube is what? 1. Because 1 times 1 times 1 is 1. The next perfect cube is not 27. There's one before 27. Who said it? 8? Carolyn, was that you? Nika, was that you? 8. 2 times 2 is 4 times 2 is 8. Now 27. Now 4 times 4 is 16. Ooh, 16 times 4 is? 64. Good. 5 times 5 is 25. 25 times 5 is? And the voices are getting sparser. 125. Who said that? It's correct. 216 is the next one. That's 4 cubed. No, sorry, 6 cubed. 7 cubed. I like it. It's an aesthetically pleasing number. Looks pretty. It's 343. So that's 5, 6, 7 cubed. 8 cubed is 512. Another number you computer people should know. 9 cubed is 729. 10 cubed is nice and easy again. 1,000. These are the first 10 perfect cubes. I want you to know them. Memorize these. Or be able to compute them very quickly. One more comparison I want to make here to the square roots. When I took the square root of a number, how many answers did I get every time? Careful. Square root of 4 is also -2. I got a plus and minus answer here, i.e. if I took the square root of 4, that's equal to plus or minus 2. And the other piece to this is, can I take the square root of a negative number? Can I multiply a number by itself and get a negative value? No, because a positive times a positive is positive, and a negative times a negative is positive. So I cannot take the square root of a negative number yet with whatever you know. I'm going to teach you how to do that later. No square roots of negative hashtags yet. You're going to be able to in a bit. That's the number sign. I was joking when I call it a hashtag. It's number sign. We know this, yes? I had grade 9s a couple years ago who did not know that this had an alternative, like it meant number sign before it meant hashtag. I had grade 9s who did not know this, like 3 years ago. Also called the pound sign on a phone. Okay, so with cube roots, when I take the cube root of something, how many answers am I going to have? Just one. Why? That is correct. Why is it correct? And I never know which one of the three of you is talking because you all look at me, but you're all masked. So, but you're right. Why? So if there's an odd number of negative, it's only negative. If there's an even number of negatives, it's going to be positive. That doesn't actually help us at all. It's the odd number of negatives that matter. An odd number of negatives is going to be negative. The only way my square root's going to be, or my cube root rather is going to be positive, the only way for my cube root to be positive is if all those digits were positive. So I can't have a plus and minus answer here. The only way to get a negative value coming out of a cube root is if I put what kind of number in? A negative in. So these guys, you can take, I'll say it this way, negatives are, in big capital letters, allowed. So the cube root of 8 is 2, because 2 times 2 times 2 is 8. And the cube root of negative 8 is Negative 2. Because negative 2 times negative 2 is positive 4, times negative 2 is going to give me negative 8. Cool? Comments, questions, concerns? Fantastic. Flip the page. It says to list the perfect cubes from 0 to 1,000. We already did that. It is going to be empty. Okay, so we want to try and estimate these. Nika, is that a hand or are you stretching? Okay, I thought you were going to do it for us here in a second. Cube root of 45. Who wants to do this question for us? I want someone to try and tackle this. I want to estimate it using how we estimated before. Who wants to take a stab at this bad boy? It's the same procedure, except instead of perfect squares, we're going to use perfect cubes. So you want to try it? Okay, she wants to try it. Here we go. So if we're estimating this, I want to find, she says, the perfect cubes on either side of 45. So you say it again, 27 and? So now instead of square rooting them, I'm cube rooting them. So the cube root of 27 and the cube root of 64 is going to be between, so it's going to be between 3 and 4. Everything else follows exactly the same way. What's my distance between 27 and 64? Oh, there, I heard it. Someone just said it. What is it? 37. I heard 37. This distance here is 37, so that's going to become the bottom of our fraction, the total distance. The distance between 27 and 45 is, there it is, 18. Do we know our 37th fractions? Obviously. So no. So let's massage this fraction. 18 over 37 is real close to a real nice fraction. 18 over 36. Because why is that such a beautiful fraction? Because 18 goes into 36 twice. So this fraction is going to reduce to, not 2, a half. There it is. Which means our estimate then is going to become 3.5. Someone want to take everyone grab your calculators. I need to show you how to take cube roots now. Everyone grab your calculator. Okay, so actually that's not really bad one to use. Let's use this one. So which one do we want to do first? Which calculator do we want to see first? I don't care. The Texas. Let's do Texas. Okay, so on the Texas calculator, we had, it didn't have the square root button, isn't its own button. It's the alternative function on the squared button. So squared gives me square root. Does anyone know what this little symbol here gives me on the Texas calculator? This button here lets me take whatever exponent I want. So if I push this button here, let's go 4 to the power of, that's what that means, 3. I can take any power I want now, 64. But if we zoom back in here and we look closely, we can see there is a little x inside the root sign where we would put a value. So here's how you use that. Let me zoom the sucker way out again. let's use 64 here. So I would put, what kind of root do I want? I want the cube root, so I would put 3, and then I push second function, and then the any root I want button, so it'll be 3 and then x root, meaning I'm taking whatever root of the number that comes prior. This isn't 3 times, this is the third root of 64, which is 4. So that's how this is done on the Texas calculator. Comments, questions, concerns? Hearing none, moving on. Casio's next. Casio has, there's 2 options here if I'm not mistaken. No, I lied. Oh, no, there is only one. Oh, no, there is 2 options. Ah, there it is. So this one has a square root button on it. Bam, there it is. And now I can type away to my heart's content. Above the square root button is there's actually a cube root button. To access it, instead of second, you push shift. And now we want the cube root of 64, which is 4. But this doesn't help me if I do anything bigger. So let's show you how to do the any root I want button. Is this guy here. This is the any exponent I want button, and I want to access the function above it. So we're going to go shift, and we're going to push. Unlike the Texas calculator, Texas, you had to push what root you wanted first. So I wanted the third root, then I pushed the 3, and then I go find my root. The Casio is actually a lot nicer for that than the other one. I'm just going to go straight to shift, that button, and now it's created for me the notation with some empty boxes. And I can fill these boxes in however I want. If I want the third root of something, I could take the 34th root of something if I wanted to. I take the third root, and then I push the arrow button over here, and now it drops me inside the root. I go 64, so the third root of 64 is 4. For stuff like this, the Casio is really, really nice. I like the Casio. Okay? And now for all you poor people who have the sharps. Actually, for this, the sharp's really good too. Because if we zoom in here, you'll see that there is, in fact, a cube button and a cube root option. So you push second and then this button to get you the cube root function. This one, just like the Texas calculator, also has the x root button, and you use it the exact same way. So I want, let's say I want the third root, do 3 and then shift blah. That gives me 3x root. So just like the TI, I punch in 64 and I hit enter. Cube root of 64 is 4. So in this case, if you have the Casio rather, the Casio is going to be the best option here. All that to say, what's the cube root of 45? Now that you all have calculators out and can use them, someone find me the cube root of 45. So this value actually is 3.55 what? Okay, so I'm going to round that to 1 decimal place, so it's 3.6 or 3.56. So this is a pretty good estimate. Comments, questions, concerns? Going once, twice, 3 times. Cool, I want you to do B and C for homework. Or right now. Do B and C right now. Let's do it that way. If you want, no, right now. Do B and C. You don't want me to, otherwise I'm going to teach you brand new things. I'm going to just keep teaching you stuff. You don't want me to do that yet. Do B and C right now. Actually, here's what I want you to do. This is now going to be the time where I give you to work on homework for the rest of class. I want you to do B and C. This is homework. And then I want you to flip past the blank stuff. We're going to do the blank stuff later. Flip past the blank stuff. And you'll see here a part 5 working with square roots that bleeds onto the next page. Square roots. And then there's a working with squares. This is nice and easy. I want you to do, for part 5, I want you to do all of it. So you got those 2 questions, the 2 cube questions. I want you to do all of these. And if we flip over here, for parts, and that includes these, all those. And then in part 6, part 6 is nice and relatively easy. I'm just going to get you to do odds here. down here in part 6. So you've got like 10 or 11 minutes left. I want you working on this stuff. Do the 2 cube estimating questions, and then all of these, and odds on these. And then we'll come back to these blank pages tomorrow and fill them in with actually way more useful stuff than estimating.